All right, so this week we are talking about earthquakes and volcanoes, which are two major types of hazard events that can result from the kind of plate tectonic activity that we learned about last week. So our goals for this lesson are first to understand how and why volcanoes are formed, then to explain the processes behind earthquakes, and finally to evaluate the risk to people of tectonic events. So what kind of risks are presented to people by earthquakes and volcanoes? So we'll start with volcanoes. So volcanoes are where molten rock from the asthenosphere comes to the surface. So remember that we learned that we have this thin solid layer, the lithosphere, on top of our Earth, and beneath that is a layer of molten rock called the asthenosphere. And some of that molten rock will sometimes try to come up to the surface, and where it comes out, we have a volcano. And that molten rock we refer to as magma when it's underground and lava when it reaches the surface. So it's the same material, the same molten rock. We just have different names for it depending on whether it's still inside the earth or whether it's come out onto the surface. And the eruption of that material onto the surface can take a variety of different forms. And we kind of think of them as being on a scale from one type of eruption to another, and then eruptions can fall in between these or be some sort of combination. So on the one end of that scale, we have explosive eruptions. And so the picture, let me move my face out of the way there. The picture there that you see of Mount St. Helens in Washington State erupting, it's a good example of an explosive eruption. You see enormous amounts of material being blasted up into the atmosphere from that volcano. The other end of this scale is what we call an effusive eruption. And there in the lower picture in Kilauea in Hawaii, you see an effusive eruption where you see this very liquid lava just flowing down almost like water out of the volcano. And the difference between these kinds of eruptions is a result of how viscous the lava is. And so viscous is just the fancy science term for thick. So if you have a highly viscous magma, very thick, it's going to trap a lot of gases. So there are gases among the materials that are coming out here, and they're going to get trapped and held inside until that magma reaches the surface, and then those gases can escape, kind of like a foam on a soda can bubbling over. And those gases will then cause that lava to blast up into the air. And that gives you that explosive type of eruption. If you have a less viscous material, a thinner material, then it's going to allow those gases to escape more easily. So the gases are still coming out of the volcano, but they're not propelling the lava up into the air in the same way. And so you get that effusive eruption. You get that just liquid-like flow of your lava down the side of the volcano. And these different types of eruptions give us different types of volcanoes. So if you have a volcano that's doing a lot of effusive eruptions, you can think of that lava, it's very liquid, so it's going to flow out and away from the vent of the volcano, the spot where things are coming out of the earth, flow out away from that very easily. So you're going to get a very large, very gently sloping volcano. And we call that a shield volcano because it kind of looks like a medieval shield laying on the ground, right? It curves up a bit in the middle, but is very wide, very broad. So that's what you get if your volcano has primarily these effusive eruptions. If your volcano has primarily explosive eruptions, you're going to get what's called a cinder cone. So that's a small, very steep volcano, because when you have all of that lava being blasted up into the atmosphere, it can fall back down into a steep kind of pile, and that gives you this cinder cone. Then you can also have what's called a composite volcano or a stratovolcano, and that's what's illustrated in the diagram there, where you get alternating layers because you get alternating types of eruptions. So you get an effusive eruption and then an explosive eruption and then another effusive one. So you get a mix of these types of eruptions. And that gives you a tall cone-shaped volcano. That's kind of our classic volcano that you probably think of if you just imagine a volcano. And if you slice through it, like we have in the diagram, you can see those alternating layers. So basically you get the explosive eruptions that allow it to build up into a steeper shape, and then you get effusive eruptions kind of sealing that in and hardening over top of that steeper cone to keep it in place, so that then you can add more material to it with the next eruption. So composite volcano is kind of in between. It's a combination of the broad, flattened shield volcano from predominantly effusive eruptions or the small, steep volcano that you get from predominantly explosive eruptions. So Mount St. Helens that we saw in the previous slide, it was exhibiting an explosive eruption in that picture, but that volcano overall is a composite volcano. It's had different types of eruptions over its history, which is why it's become such a big cone-shaped mountain. It's just that its most recent, very famous eruption happened to be one of the explosive ones. Another type of volcanic landform that you can find is a caldera. So when the volcano erupts, it's emptying out the magma chamber that's below it. So there's a spot where all of that magma is sitting until it builds up enough pressure to erupt out of the volcano. And so after the eruption, that magma chamber is going to be emptied. And it's possible that the sides of that magma chamber may be weak enough that the weight of the volcano, once the magma chamber is empty, will kind of collapse down into it. And you'll get a big crater-shaped formation, and that's called a caldera. So that the top of that volcano collapses back into the empty magma chamber and gives you this big crater. But more magma may come along, and so you may get then a new volcano forming in the middle of the caldera. So if we look around the Earth at where we find volcanoes, this map shows current active volcanoes in the world. We find they're not distributed equally across the world. There are some places where we get lots of volcanoes, other places where we get very few. And so if we take a look at this map, we'll notice some of the areas that we're seeing a lot of volcanoes. We have all along the west coast of both North and South America, and then across the Aleutian Islands, and then through some of the island chains on the east coast of Asia. So around Japan, through the Philippines, Indonesia, etc. We get a lot of volcanoes there. You'll see there's a lot of volcanoes in the Mediterranean. We've got a lot of volcanoes in Iceland, and then kind of spotted down through the center of the Atlantic Ocean. And we've got a bunch of volcanoes in Eastern Africa. And if you take this map and you compare it to some of the maps that we looked at last week, you may notice that a lot of these places where we're seeing large numbers of volcanoes are along the boundaries of tectonic plates. And in fact, many of our tectonic plate boundaries are characterized by volcanoes. So if we have an ocean-to-ocean convergent plate boundary, we get subduction of one plate under the other. The material that's being subducted melts in the asthenosphere, and then it tries to return back to the surface because it's a less dense material. That's why it was making up the lithosphere in the first place. It was less dense. And you shove it down into the asthenosphere, melt it, it's going to try to come back to the surface. You're going to get volcanic islands. So that's what you're seeing in places like Japan or the Philippines or the Caribbean, are volcanic islands formed by these ocean-to-ocean convergent plate boundaries. You are also seeing them at the ocean-to-continent convergent plate boundaries, because again, you've got subduction there. The oceanic plate is getting subducted under the continental plate, melting, materials returning to the surface in the form of volcanoes. Those volcanoes are just forming on a landmass rather than on an ocean, and so you get volcanoes on land. That's what's going on up and down the west coast of the Americas. We're also getting volcanoes at divergent plate boundaries, where two plates are spreading apart. They're leaving a gap there, and so magma from the asthenosphere is going to come up and form a volcano to fill in that gap. So when we saw Iceland and all down the center of the Atlantic, that is a major divergent plate boundary. Right? The sides of the Atlantic are splitting apart from each other, and so we get volcanoes there. And that also explains those volcanoes we saw in East Africa. That's a place where the African continent is starting to split apart. We're getting a divergent plate boundary there, and so volcanoes are occurring as the Earth is kind of filling in that gap that's forming in the lithosphere. We're not seeing volcanoes at two other tectonic plate boundary types. One is a continent-to-continent convergent plate boundary. So if we skip back, if you look at the Himalayas, for example, between India and China, you'll see that big white spot in the middle of Asia there. That's the Tibetan Plateau, and along the south of it is the Himalayas. And you don't really see volcanoes there because the continent-to-continent convergent plate boundary, there's no subduction. Nothing's being pushed down into the asthenosphere, so there's no material being melted that could fuel those volcanoes. And likewise, at a transform plate boundary, if the two plates are sliding past each other, again, nothing is being pushed down into the asthenosphere, so there's no source of material that would form volcanoes. So 3 out of our 5 plate boundary types are characterized by volcanoes. Volcanoes are one of the ways we identify where those plate boundaries are, but our other plate boundary types aren't typically associated with volcanoes. And there's one more way that we can get volcanoes that isn't associated with plate boundaries, but is still connected to our understanding of the interior structure of the Earth. And that's something called a hot spot. So a hot spot can form right in the middle of a tectonic plate. And there we have what's called a mantle plume. So we have a bunch of magma from the asthenosphere just trying to come up to the surface at one particular spot. And we still don't totally understand why these mantle plumes form in the places that they form. But we know we have a bunch of them scattered around the Earth. Just a spot where magma from the asthenosphere is just trying to get through to the surface. And it breaks through whatever plate is sitting on top of it and forms a volcano at that spot. And so a few examples of hotspots that we can see on the map here. One of the most famous is Hawaii, smack dab in the middle of the Pacific Ocean, middle of the Pacific Plate. No plate boundaries for thousands of miles, but we've got a hotspot that's forming the volcanoes that make up the Hawaiian Islands. We've got another famous hotspot in the western United States underneath Yellowstone National Park. That's something you'll be looking at in your exercise for this week. There's a hotspot there. It has produced volcanic activity in the past. It's also driving all of the cool features of Yellowstone, like the geysers and hot springs and so forth. The heat that produces those comes from the magma in that hotspot. There's also a hotspot under Iceland. So Iceland has two things going on. It's got a divergent plate boundary there as the Atlantic Ocean is separating, and you've got a hotspot right under Iceland. So that's why you get so many more volcanoes there than down the rest of that divergent plate boundary. And there are a bunch of other ones that aren't as well known scattered around the world. It's typically what you're looking at when you see a significant amount of volcanic activity in a spot that's not associated with a plate boundary. So this mantle plume comes up, it breaks through the plate that's above it, and it forms a volcano there. But that plate is still moving relative to the mantle plume. So the mantle plume is going to stay in place, and the plate is going to move over it because all of our tectonic plates are always in motion. And so eventually that volcano is going to get dragged away from the mantle plume. And so now it doesn't have a source of magma anymore. And the volcano is going to go extinct. It's going to stop erupting. And a new volcano is going to form at the spot on the plate that's now over top of the mantle plume. So you're going to have an old volcano kind of downstream in the direction that the plate's moving, and then you're going to have a new volcano forming upstream of that. Then eventually the plate's going to move more, and that newer volcano is also going to go extinct as it gets pulled away, and another new volcano is going to form over the mantle plume. So a characteristic thing that we see when we see a hotspot is a chain of volcanoes where you have an active volcano still being fed by that mantle plume at one end, and then your volcanoes get progressively older and older and older as you go away from that spot where the mantle plume is. And so the illustration there shows this in the case of Hawaii, which is one of the clearest examples of this. So we have several current active volcanoes on the big island of Hawaii. Mauna Loa, Kilauea, and then we've got Loihi, which is a sort of brand new one just forming off the south coast of the Big Island. Those are all actively being fed by that mantle plume, so they erupt from time to time. But then if we go upstream from that, in the direction that the plate is moving, we get to the island of Maui. And we can date the rocks on Maui. Maui is about 1.3 million years old. So that tells us about 1.3 million years ago, Maui was over that hotspot, and the Big Island didn't even exist. It hadn't been formed yet, because the Big Island just is those volcanoes, and they've gotten big enough to stick out of the water. Right? So 1.3 million years ago, Maui was over the mantle plume. Big Island didn't exist yet. Continue going upstream, we get to these other islands, and they get progressively older, right? Molokai is 1.8 million years ago. Oahu is 3.4 million years ago. Kauai is 5.6 to 4.9 million years ago. And then if we keep going in that direction, we run out of islands, but we find what are called seamounts. So these are mountains on the seafloor that just aren't big enough to stick up out of the ocean. Because these older volcanoes, the older they are, the more time they've had to erode. Right? They're no longer being built up by new eruptions coming from that mantle plume. And so wind and rain and waves from the ocean are going to start eroding them down, and they're going to get smaller and smaller until eventually they're small enough that they no longer stick out of the water as an island anymore. So by tracing the direction of these older volcanoes and looking at the ages of them, we can tell the direction and the speed of movement for the Pacific Plate. So these hotspots have been very important in helping us to understand the movements of our tectonic plates. They form kind of a record of where that plate has been and how long it's been moving in that direction. So if we get in a volcanic eruption, there's a lot of things that can happen to us, many of them bad, but some of them good. So the most obvious hazard presented by a volcano is the lava flows. Okay? The lava comes out of the volcano and it flows down and it buries things, destroys things. The speed of that lava can vary greatly. So sometimes that lava is slow enough that you could actually outrun it if you happen to be in its way. I wouldn't recommend it. It's a big risk. You might trip and fall. But sometimes that lava is moving slow enough that you can get out of its way, but you can't really stop it. And so if your house is in the way, your house could get buried in lava. If there's an important road in the way, the road gets buried in lava and destroyed. If your farm is in the way, your farm gets buried in lava and destroyed. We also have what are called pyroclastic flows, and these are some of the most dangerous outputs of a volcano. So pyroclastic flows are flows of gases and rocks that are ejected from a more explosive kind of eruption. And they can move much faster than the flow of lava on its own. So they can easily just sweep through where people are and catch you off guard. You have no time to escape and kill you, destroy everything that they land on. There are also toxic gases. So I mentioned, one of the things that creates the differences between the different kinds of eruptions is these gases that are trapped in the magma and how they, how trapped are they in that magma and how do they escape when they get out. Well, those gases are often very toxic. They're not something that you or animals and plants and stuff really want to be breathing in. And so those can cause a lot of death and other problems. We also get acid rain and ash fall. So Some of the material that comes out of the volcano ends up right back down on the ground pretty quickly. Others of it gets thrown up into the atmosphere and can be carried quite a good distance in the atmosphere before it finally falls back down to Earth, either in the form of volcanic ash, like solid pieces coming down, or in the form of acid rain. So it gets dissolved into raindrops that form up in the atmosphere and carried down in that form. And so then that rain is bringing with it these other chemicals that are often highly acidic. That's not good to get caught in. The picture there shows the result of ash fall on a U.S. military base in the Philippines. And so you can see there are all these big buildings there, and that one in the center, the roof has just been completely crushed by a few feet of ash that settled on that roof. So this area escaped the direct impacts, the lava flows and things, but this ash fall landed on this and smashed a lot of these buildings that were there. Volcanoes can also cause forest fires. There's a lot of heat. That lava is incredibly hot. The pyroclastic flows are incredibly hot, and they can light things on fire. They can start a forest fire. It's one of the sources of a naturally ignited forest fire aside from lightning. And so those forest fires can spread even farther than the materials that are directly coming out of the volcano. You also get what are called lahars, and these are mudslides triggered by volcanoes. And so there's kind of two ways this can happen. One is if you have a lot of snow and ice in the area where the volcano is erupting. Right? Some of our volcanoes are in tropical areas, but if they're big enough, there may still be snow and ice on top of the volcano itself. And then, of course, we have volcanoes in places like Iceland and Alaska where it's snowy at all elevations. But there's so much heat that comes out of the volcano that it can melt that snow and ice, and that loosens up all of the soil and rock that surround it, and it can come flowing down the side of the volcano as this very dangerous mudslide. This can also be triggered when you have a whole bunch of ash and pyroclastic material that are deposited as a result of a volcanic eruption that's often very unstable. It's just laying there kind of in a loose pile. And so then if you get a heavy rain right after your volcanic eruption, then that rain can waterlog all of the volcanic ash and cause a mudslide from that. So there's a lot of bad things that can happen if you get caught in the path of a volcanic eruption. But I do want to highlight one good thing that comes from a volcano, and it explains why so many people around the world live in close proximity to volcanoes. So a lot of these places that we have volcanoes are also places where lots of people live. Right? Lots of people live in Hawaii. Lots of people live in Japan. Lots of people live in the areas of the Mediterranean like Italy that have a lot of volcanoes. Why would people spend so much time living close to volcanoes? Because all of this new material that's deposited by these volcanoes can make for some very rich soil. So renewing your soil, adding new material to the soil is how you maintain the fertility of it. And so areas close to volcanoes often have very fertile soil, can grow a lot of food there and support a lot of people. Volcanoes are necessary to maintaining this soil fertility in a lot of areas of the world. So it's very bad to be right in the path of a volcano when it's erupting. But if there have been past volcanic eruptions in your area, then that may provide you with some really great soil and make a really good reason to be living in that area. So now let's talk about earthquakes, our other major type of tectonic hazard. An earthquake is essentially the sudden movement of tectonic plates. So when our tectonic plates are moving, they're not moving just smoothly past or over or away from each other. Their motion is kind of jerky. They get stuck for a little bit, pressure builds up, and then they jump forward a little bit. And then they get stuck and pressure builds up, and they jump forward a little bit more. And each of these times that they jump forward a little bit, that they break through whatever had them stuck and move a good bit of distance in a short period of time, gives you an earthquake. It creates vibrations in the earth that spread out from the point where that motion happened. And so if we're trying to identify where an earthquake comes from, we sometimes talk about the focus and the epicenter of the earthquake. So the focus is the point at which the greatest movement happened. So that's going to be somewhere along the fault line that separates our two tectonic plates. So the two tectonic plates meet at this fault line, and somewhere on that fault line is where that motion originated from. That's the focus of the earthquake, and all of the waves of the earthquake spread out from that focus. The epicenter is the spot on the Earth's surface directly above the focus. So the focus is usually somewhere deep underground. So the epicenter is the point on the surface directly above the focus. Since we live on the surface, we want to know, right, that surface point above the focus. And the name epicenter comes from that idea. Epi meaning above, and center being the center, the focus of the earthquake. So the epicenter is just the point above the center of the earthquake, the spot on the Earth's surface above that focus. And we measure the strength of earthquakes using what's called the moment magnitude scale. Now, you've probably heard of the Richter scale. The Richter scale is essentially an older version of the moment magnitude scale. So it's been updated and revised. So moment magnitude is what seismologists, people that study earthquakes, use today. It's the same basic idea as the Richter scale. It's just a sort of a new and improved version of it. And what the moment magnitude scale really measures is the amount of energy that's released during an earthquake. So an earthquake is a release of an enormous amount of energy. So those plates have gotten stuck and they've built up a lot of pressure, and it's released as a large amount of energy as they finally move past each other. So if we measure the amount of energy that's being released, that tells us the moment magnitude of our earthquake. So it's measured on a scale going from 0, which would be no earthquake happening, up past 10. And this is a logarithmic scale. So what that means is that every time you go up one number on the scale, you have multiplied the amount of energy involved by 10 times. So if you have a 4 magnitude earthquake, and then you have a 5 magnitude earthquake, that 5 magnitude earthquake has 10 times the amount of energy as the 4. And then if you had a 6 magnitude earthquake, that would have 10 times the energy of the 5 and 100 times the energy of the 4. So it's not a linear scale where each number you go up is the same amount of increased energy. You're multiplying by 10 every number that you go up. And you can see on the graph there exactly the amount of energy that means. We're not going to worry too much about quantifying the exact amount of energy that is going on, but we want to understand the difference in going up one notch on that moment magnitude scale, that it's a factor of 10 increase. And another important thing to note is that you get more earthquakes at lower moment magnitudes. So we are surrounded by earthquakes in the vicinity of 1 on the moment magnitude scale. Those happen all the time. The Earth is always readjusting by this tiny little bit that we couldn't even feel. It takes at least about a 4 moment magnitude earthquake for a person to really be able to feel it. Below that, it can be detected by seismometers, by instruments that measure those waves in the Earth. But a person's not really going to feel it until it gets to about a 4. So we've got, per year, 1 million earthquakes worldwide that are a moment magnitude 2, and they just go right over our heads or below our feet. We don't even notice them. But then as we get into some of the larger magnitudes, they become rarer. We get fewer of them each year, but they also get so much more energy that they have the potential to be much more destructive, to do a lot more damage to people and things when they occur. And so those are the earthquakes that we get really worried about, the really high moment magnitude ones, because they have the potential to cause a lot of damage and a lot of problems for us. So when an earthquake happens, it releases waves. So the shaking in the earth is the form of waves moving through the earth. And there are four main types of waves that are just different ways that the earth is moving. And they move at different speeds. So one type of wave will hit you before the next, And the farther out you are from the earthquake, the more separation there will be between when these waves get to you, because there's more time for those speed differences to be manifest, but also the weaker they'll have gotten by the time they get to you. So the first wave that you would get hit with, it's called the P wave, P for primary because it's the first one, and it's a wave of compression and expansion. So your ground is squishing and stretching in and out as it moves from the focus of the earthquake. And this is a very fast wave. It can move up to 500 meters per second. All right, so this is moving very fast out away from that focus. So the P wave is this expansion and contraction kind of motion. Then you get the S wave, S for secondary, because it's the second one. And this is an up and down movement, or a side-to-side movement of the ground, right? So instead of squishing and stretching like the P wave, it's moving up and down or side to side. And so that's going to move slower than those P waves, so it's going to hit you second. Then you get the Rayleigh wave, which is a rolling motion at the surface. And you can compare this to waves on the ocean. So on the ocean, right, those waves aren't actually the water in those waves isn't going anywhere. It's just going up and down in one spot. And so that's what the Rayleigh wave does to the Earth. It just circles it around like a wave on an ocean. That's moving slower than the S wave, so that'll hit you third. And then the fourth one, the slowest moving one that will hit you last, is the Love wave, which is a horizontal movement at the surface. And so hopefully the pictures there clarify what I'm saying a little better than my words. I think it's easier to picture it than to have me try to describe it, right? So we've got these four different kinds of waves happening one after the next that create different types of movement, different types of motion in the earth as they pass through. And so these waves spread out away from the focus of the earthquake, and they spread out along the surface of the earth and also down into the earth. And so these waves are one of the ways that we actually know what's going on inside the earth. So in the last lesson, we talked about the interior structure of the earth, these different layers that the earth is made out of. And I also mentioned that we've never actually dug down below the crust of the earth, right? We've never dug down into the mantle, certainly not down into the asthenosphere. So how do we even know what's down there if we've never been? Well, we can infer the interior structure of the earth from the movement of seismic waves from an earthquake to other parts of the earth. So those waves are moving out in all directions, including down through the earth. But the speed and direction of those waves is going to be affected by the composition of the materials that they pass through. So when those waves hit a discontinuity, when they hit a change in the material that exists inside the earth, then they may get deflected, they may change direction, or they may get blocked entirely. So S waves, for example, can't pass through liquid. So they're blocked entirely by the liquid outer core. And we get this kind of shadow on the opposite side of the Earth, where seismologists aren't going to pick up any S waves from an earthquake that happened opposite them on the Earth. Then our P waves can get through, but they're going to be deflected. And so they're not going to come straight through the center of the earth. And so again, that direction, which we can judge by the amount of time it takes to get through the earth, is going to tell us something about where these boundaries are located within the earth. So it's the movement of these seismic waves through the inside of the earth that helps us understand what's going on deep down there, where we can't actually, dig down and look at it directly ourselves. So earthquakes are, as we said, generated by the movement of tectonic plate boundaries. And so we can look around the earth and see earthquakes basically showing us where all of our tectonic plate boundaries are. If you were to take this map and compare it to the tectonic plate boundary map from last lesson, you'd seen it lines up very well. So we get earthquakes along all kinds of plate boundaries. Because all of our plate boundaries involve those plates moving relative to each other, whether it's one getting shoved under another or one pulling apart from another or moving past each other. All of those motions cause earthquakes. All of those motions are not going to be smooth and steady. They're going to be a little bit jerky, and we're going to get earthquakes happening. So we see earthquakes at convergent plate boundaries, divergent plate boundaries, and transform plate boundaries all around the world. So some of the biggest ones happen where there's that subduction, because there's just a lot of stuff scraping past each other, a lot of potential for it to get stuck for a while, build up a lot of energy, then release it all at once in a big earthquake. So that's why you see the west coast of the Americas having a lot of very large earthquakes here, along the eastern side of Asia, in Japan, Philippines, etc. Lots of earthquakes there, but you also see them along all of the other plate boundaries as well. So just like with volcanoes, we can look at what are some of the hazards that result from earthquakes. So the first and most obvious one is falling debris. You are, in your house, and an earthquake happens and stuff falls, and the stuff can break and the stuff can hit you. You might fall and get injured from that. A whole building might collapse. If the earthquake is strong enough and the building is weak enough, the building can collapse, trees fall over, etc. We get damage to infrastructure. So earthquakes can cause collapse of bridges. They can cause destruction of roads, gas pipes, water pipes. Earthquakes can empty reservoirs. So if you've got a dam, for example, that's holding back a big amount of water that might be an essential water supply for a community or a city or something, an earthquake could breach that dam, or could create a gap somewhere else around the reservoir that drains that water out, which then creates this secondary hazard of a big flood coming down, as well as a long-term problem with lack of that water. Earthquakes can also redirect streams and alter the hydrologies of places, misalign aquifers, and so forth. So earthquakes can present a threat to availability of water supplies. And then earthquakes can also trigger tsunamis. So if your earthquake is happening underwater, if that the motion, if the shaking, the waves that come from that earthquake are just right, they can trigger a giant wave in the ocean. It forms a tsunami and can wipe out coastal areas very far from that earthquake. So one of the more famous tsunamis in recent history, and that's what's the picture there comes from, is the Boxing Day tsunami in 2004 in the Indian Ocean. So it was triggered by an earthquake off the coast of Sumatra in Indonesia. But the tsunami spread all around the Indian Ocean. So people thousands of miles away from that earthquake got hit very badly with this tsunami. So I've been talking about these potential hazards that come from a tectonic event like a volcano or an earthquake. But I think it's important to understand the connection between a hazard and a disaster. So earthquakes and volcanoes are the kind of things that people often refer to as natural disasters. Or a volcanic eruption or an earthquake is a natural disaster. But in the field of disaster studies, among scientists that study disasters, we commonly say there is no such thing as a natural disaster. There's no such thing as a natural disaster. And what we mean by that is that natural processes alone don't create a disaster. Because a disaster is the loss of things that people value. So that could be human life, health, property, community, the environment, all these things that we might value. If we have a catastrophic loss of them, or a big loss of those things, we call that a disaster. And so a disaster is going to occur at the intersection between a hazard event, which may be entirely natural. You have a natural hazard event like a volcano. People can't control volcanoes. People can't have really any influence on when and where volcanoes erupt. So that's a natural hazard event. It becomes a disaster when it intersects with human values that are vulnerable. with things that we care about that are in the path of that disaster. And that vulnerability is the product of human choices: where to live, how to build, how to distribute resources, etc. So a disaster requires a combination of the hazard event, which might be natural, with vulnerability, which comes as a result of human choices. So that's why there's no such thing as a natural disaster. Disasters are only partly the result of natural forces. They're also partly the result of things that people are doing. The vulnerability that we have to being harmed by things like the shaking of the ground and a pyroclastic flow or whatever other features are coming from our hazard event. So to illustrate the importance of vulnerability in shaping a hazard event into a disaster, we can compare two earthquakes that happened in the Americas in 2010 within a couple months of each other. So first we had an earthquake in Haiti. And this was a 7.0 on the moment magnitude scale. So this is a pretty big earthquake. And this earthquake resulted in 230,000 deaths. So this was an absolutely devastating earthquake, killed an enormous number of people, and there was a ton of loss of money and property and buildings and stuff on top of that, and many more people injured and so forth. So this was just an absolutely devastating earthquake in Haiti. Then in the country of Chile, we had an earthquake that was an 8.8 moment magnitude. So if you remember, the moment magnitude scale is logarithmic. So an 8 moment magnitude would be 10 times bigger of an earthquake, 10 times more energy released, 10 times more shaking of the earth than a 7. And then a 9 would be 100 times more energy released and 100 times more shaking than a 7. So this earthquake in Chile was almost 100 times bigger in terms of the amount of energy released, in terms of the geological dimension of the earthquake. But only 531 people died in Chile, despite the fact that the earthquake hit in Santiago, like the biggest city in Chile. This wasn't happening in some remote wilderness area where there just wasn't anybody around. The difference is vulnerability. The difference is that Haiti is a much poorer country than Chile. And so in Haiti, people didn't have the resources to respond to earthquakes. They weren't able to build their homes in ways that resisted earthquakes and that were up to modern building codes and engineering standards to the same degree that people in Chile were. They weren't able to mobilize rescue operations to pull people out of the rubble the way that they were in Chile. So the poverty experienced in Haiti led a smaller earthquake to become a much bigger disaster when it struck. And we find that typically those who are worse off in society as a whole, so people who are poor, women as compared to men, racially marginalized groups, and so forth, right? Any group that is overall worse off in society, that is on the short end of the stick in terms of social inequality, is usually going to be more vulnerable to whatever kinds of hazards might exist in that place, whether it's a volcano or earthquake or hurricanes or forest fires or whatever other kinds of hazards may occur in that place. People who are worse off in society tend to be more vulnerable, and so they will experience a worse disaster from the same hazard event as people who are better off in that society. So social inequality plays a huge role in the vulnerability of people to various sorts of environmental hazards. So for your lab assignment this week, you are going to be evaluating some information about tectonic hazards. You're going to be looking at a case study of that hotspot that I mentioned in Yellowstone and trying to understand the types of hazards that might present, and then the possible social responses to those hazards. What could we do to prevent a hazard from turning into a disaster?